So this is what you do. Sometimes the pattern's not so easy. So you look at the numbers, you look at the numbers, you look at the numbers. Do you see much of a pattern there? Probably not. And so other things you do are to do what? You try like graphing it, right? Or you could try a number of other things. And so to make a long story short, figure out the mathematical pattern of this wasn't easy, but it's entirely empirical. You don't have to understand what's happening. And so the mathematical equation that came from these first 10 numbers is given by this expression here. But this expression here is based on wavelength. And so it's a kind of a weird problem because here they have frequencies and the pattern that they got is for wavelength. But we know that wavelength and frequency are related by what? Yeah, speed of light. So frequency is equal to c over lambda. Or lambda is equal to c over frequency. And so we can relate frequency and wavelength here. Now, normally, if we have the data in frequency, then we come up with an empirical equation in frequency. And there is actually an empirical equation for this in frequency. It's another variation of the Rydberg equation written in terms of frequency. But we could also have the Rydberg equation in terms of wavelength also. And so there are three versions of the Rydberg equation. Three versions are energy of the photon, which is the equation we have in the book and the equation I used on the board. That's probably what I recommend remembering. I don't recommend remembering all three equations because it's not worth it. You know, they have different constants. Like, for example, if we want energy, they have the Rydberg constant. If we want frequency, they have another constant. If you want wavelength, they have another constant. We can figure out what the constant is, but, you know, it's not worth it. It's probably best just to remember one equation, the energy equation, and then if I need the frequency, that's easy to determine, or if I need the wavelength, that's easy to determine. And so we have this. Energy is equal to h nu, which is equal to ac over lambda. And so we can relate it to that. All right, so to give you a little bit of historical perspective, then they come up with these equations that relate to frequency or the wavelength. And so basically what somebody did was they looked at the pattern of wavelengths. And from the pattern of wavelengths, they come up with this empirical equation that seems to work. And this is where m and n are integers, and m in this case has to be greater than n. And so this is not an emission. This is an absorption, what we call it. Or there's a negative sign that's missing here, you know, because the energy is negative. And so, well, this gets a little bit tricky because it would be, if it were emission, it would be negative. And if we have a negative wavelength, what does that mean? A negative wavelength doesn't mean anything necessarily. So usually what we do here is if we're interested in the wavelength, and this is the only case we do it, is we would do it, the lambda is equal to hc over e. In this case, you'll often see this. People will take the absolute value of this because having a negative wavelength is weird. How could you have a negative wavelength? The smallest wavelength you can have is 0. But what negative wavelength would mean is that you would be emitting light of that wavelength rather than absorbing light of that wavelength. And so to avoid this possibility of having a negative wavelength, people usually do this. Another common way that this equation is written is written as hc over delta E. But delta E and E are the same thing because this is the energy of the photon that's going to be emitted due to that transition. And so this is the equation that they have here. What Petrucci likes to do is he likes to always keep this in positive. And so he'll often change the sign of this, but that's all right. We'll do this. So if you were to derive the equation for lambda from the Rydberg equation, you get something like this, except the sign is wrong. And the sign's wrong because he swapped these. So it's initial minus final to keep it positive. But I don't like that mathematical trick. I'd just rather take the absolute value and just do final minus initial. I'm going to do that, try to get a positive wavelength. But making the story a bit longer, basically what we have here is just the numerical equation that fits that. And so if we want the equation in terms of frequency, then we just take C and divide it by that equation there. So this is going to be C divided by B m squared over m squared minus n squared. And so this part A is just coming up with an equation that is in terms of frequency instead of lambda. Once we have that, then we could use that equation to try to predict these lines here and then figure out what those transitions are. Does that kind of answer the question? For part A, they just want an equation in terms of frequency instead of wavelength. So we need to know the relationship between frequency and wavelength. So here, we're just going to solve for frequency. We have the equation for wavelength. We'll just plug it in substitution-wise, and then we get that. So that's relating it. We have all the, the equations. If you look at the if we look at the equations, we have different equations. So, for example, this is our normal equation here, delta E or E. Well, we also have equations in terms of lambda, although we got to flip this one over. Let's see if I have it. And we also have equations in terms of frequency. That you can find, or you can solve. So does that make sense for part A? Part B, use the expression you derive in A to calculate the expected ratio of the frequencies of the first two lines in each of the Lyman, Balmer, and Pashon series. So here, this is the frequency for the 2-1 transition. And so they want us to take the ratio of the frequency of the 2-1 transition over the frequency of the 3-1 transition and see if there's a pattern there. Oftentimes we do this when we're looking for patterns. We just try different things. So sometimes we'll square it, sometimes we'll take the square root, sometimes we'll do it. And all they're doing is they're looking for a ratio. So if you take the 2-1 transition over the 3-1 transition, what do you get? And so this is the ratio. Compare your calculated ratios to the observed ratio. So this is the observed ratio. So what they're saying is that, okay, if we take the ratio of the 2-1 to the 3-1, so 2-1, second floor to the first floor, third floor to the first floor, we get a ratio. And then we take the third floor to the second floor over the third floor to the first floor, and then the fourth floor over the third floor, and fifth floor over the third floor, and then look for a pattern. Do we see a pattern? The pattern is, do those ratios are they the same, or is it just some random number? If they're all the same, then there's something to this pattern. And so this is the whole gist of this problem is just that this is looking for patterns. That's all. And so this is like the first step of the scientific, well, second step of the scientific method. Second step of the scientific method is to is to is to look for the patterns. And so if you're given data like this is our observation, this is a line spectrum. Do you see a mathematical pattern here? It's not so easy, right? How would you see a mathematical pattern to this? You know, it could be hard. For this one, I don't know. This is a hypothetical, but maybe there is no pattern there. But it turns out that, you know, hydrogen's got a lot simpler spectrum. So when we look at the spectrum for the hydrogen atom, take a look at that. Where is that spectrum at? Here it is. When you look at this, do you see a pattern? It doesn't look like it, but there is a mathematical pattern. There's a mathematical pattern to the wavelengths, there's a mathematical pattern to the frequencies, and there's a mathematical pattern to the energies. And so if we're doing wavelengths, then we can come up with the equation for this. But was it an easy thing to determine? No, it wasn't so easy. When you look at it, it's hard to see, and it's surprising that somebody figured it out. You know, and they figured it out. The pattern turned out to be this. It turned out the energy of each of those lines is equal to a constant. So this is a minus constant times 1 over n final squared minus 1 over n initial squared. Do you see this mathematical pattern in that? Where n is an integer from 1 on? No, I don't see it either, but somebody did. You know, somebody spent a lot of time trying to figure it out. And so the reason why I assigned this is not for you to actually sit there and figure it out, but for you to just look at these numbers and then see, is there a pattern to it? It turns out, yes, there is a pattern to this number. And in terms of wavelength, that would be the, oh, did I erase it? Yeah, I erased it. In terms of wavelength, that mathematical pattern we just wrote down, that was from A, but that it's kind of backwards because the mathematical pattern would come first. Oh, actually, here it is. This is lambda, but this is in frequency. And so the mathematical pattern and frequency would come first, and then we can figure out that in terms of lambda, this would be it. And then we can figure out in terms of energy. B and C and D and E are all kind of the same thing. So for this particular problem, it's not necessarily being able to recognize those patterns. It's not so easy to recognize those patterns. Like the hydrogen, I wouldn't ask you to derive the Rydberg equation based on 4 lines in the hydrogen spectrum. It would be quite a lot of work. It wouldn't be so easy to do. But what you could do is you could just read the question and then just skim the answer and then just write little notes to self. Oh, I didn't have the answer for it? Oh, all right, then you can't look at the answer. So in this particular problem, it's just to say that there's more mathematical patterns in there that somebody figured out, and you have to dig deeper for that. You know, how did they know that these ratios would come out the same? You know how they figured it out? They just figured it out by guessing and checking it. And so this is like guess and check. You know, you could look other ways you could fit things. To show you another example, this is one from Chem 1B. If you look at the line marked equilibrium here, do you see a mathematical pattern to these numbers here? These numbers are what we call the equilibrium concentrations of this copper 2, tin 2, copper 1, tin 4 in this chemical reaction here. This is a redox reaction. And after this reaction's done its course, this is where it ends up. And then they repeat the experiment, but they use different starting points. And this is where it ends up. And then they repeat it again, and this is where it ends up. And so do you see a pattern to that? Well, what one person might do is they might try to graph it. And when you graph it, you're looking in the gray region. Do you see a pattern there? It goes blue, black, magenta, green. Do you see a pattern there? Blue, black, magenta, green? No. I don't see a color pattern there if we label it colors. Do you see a mathematical pattern in the numbers? It doesn't look like it, but you know what? There is a mathematical pattern to the numbers. Can you tell me what it is? No, you probably can't tell me what it is because it'd take a heck of a lot of work to figure it out what that pattern is. And it turns out it did take a heck of a lot of work, and then finally people figured it out. They tried a whole bunch of different things. Like they tried to put the concentration of the products over the reactants. That didn't work. And then they tried to double the copper concentration and both, and then tried to see if there's a ratio there. That didn't work. And then kept trying different things until they found something that worked. And do you know what the pattern that worked was? The pattern that worked was if they squared this third line here, if they squared it, like 640, and they squared that, and then 0320, and then divided, and they squared the copper, and then left the tin alone, they got 149. And then they had totally different conditions here, but it ends up at, okay, then look at the numbers here. You see when we do that, we get 148. And then in the final one here, we get 148. And so there is a pattern. There's a mathematical pattern to those numbers. You just didn't see it, and it takes some work. And so that particular problem is a hard problem because, how are you expected? You aren't expected to derive it. They're giving you so many hints to try to figure out what that equation is. But basically that equation turns out to be the Rydberg equation. All right, and so that's good enough. There's no answer to that, so. Yeah, the point was to illustrate that it's not so easy to look for these patterns, and you have to do a lot of digging to get to them. Sometimes the pattern is very easy, like Beer's law. That pattern is very easy because it's linear up to a certain point. So don't worry too much about that particular question. Somebody else figured out the pattern and gave you the equation, so we don't have to do that. And the empirical equation or the law is Rydberg law. That's what it comes out to. And then we could do lots of variations of the Rydberg law, but there are additional patterns in there. You could call it the law of the ratios. The law of the ratios is what they did. They said it's obvious to see, but it's not so obvious to see, was it? I don't think it was so obvious. Okay. Other questions? But if it was so obvious, then science would be very easy, and anybody would be able to do it. Maybe you throw those numbers into, let's say, ChatGPT and ask for it to find all the mathematical patterns in the numbers. Maybe it could do it. Pretty sure it should be able to do it, I would think. For the first 3 numbers, ask it to find the remaining 7. Or the first 2. Maybe the first 2 wouldn't be enough. Ask it to find the remaining 8. So the test tomorrow is going to be with chapter 7 and chapter 8. And there's going to be a little bit of extra stuff. Not from 9, but from 10? No, 11. Chapter 11. And the extra stuff is because we're dealing with atomic orbitals. And so we want to know all the atomic orbital energy level diagrams. And so what atomic orbital energy level diagrams do you know so far? You know the hydrogen atom, or the one electron species? Do you know the multi-electron species? You do? Do you know the one that I did on the board, or do you know the one in the book? Okay. It's good. If you know the one I did on the board.
We never did the exceptions though. Like on chromium.
Oh, we didn't?
No, we didn't get there.
All right, so I'm still on chapter 8 then. We'll talk about the exceptions. But you need to know how to draw the orbital energy level diagram to the fourth shell. There's a problem with this one though. What's the problem with this one here? Well, it has part of the fourth shell. Part of the fourth shell would be the 3D. Yeah. And so what's missing here is the 4F. And then the 4P. And so you need to be able to draw this. For atoms, what we call free atoms, this is what we see. This is what we observe. So for multi-electron free atom, we're going to have the 1s, also known as the 100, and then we're going to have the 2s. There's going to be a big jump between the 1s and the 2s. This is 200. And then the 2p, where there's going to be a small jump up to the 2p. Okay. 2p is going to have the 2, 1, negative 1, 2, 1, 0, and 2, 1, 1. And then the 3s is 300. And then the 3p, which consists of 3, 1, negative 1, 3, 1, 0, and 3, 1, 1. And then what? Yeah, the 4s comes next. Why is that? Why isn't it the 3D? Yeah, 4s is more penetrating than 3D, even though 3D should have a most probable distance with electron closer. The reason why people write it offset like this is to have different L's. So over here we have L equals 0, which is the s orbital. And then here we have the L equals 1, which will be the p orbital. And then over here we're going to have L equals 2. And so they write it like this, and then furthermore, what they can do is they can write the m value. And so the m values would be over here, m, negative 1, 0, and 1. Like that. And so they can spread it out. Over here we'd have, for the 3Ds, we'd have what? 3, 2, negative 2. So L is equal to 2. Our first m value is going to be negative 2. So here m is equal to negative 2. And then what's the next m value? 3, 2, negative 1, 3, 2, 3, 2, and 3, 2, 2. And so usually it's spread out like this. That has quantum mechanical orientation. It's weird, but there's things called selection rules or transition rules. also called the angular momentum quantum number, and that is this conservation of angular momentum. So, for example, you might not know this, but an electron can't drop from a 3s to a 2s. An electron has to drop from, let's say, a 3p to a 2s. Or of that sort, or an s to a p, that would work as well. And so there's certain rules. And so this is another reason why. The rules we aren't going to get into. And then the 4p. We also have the px, py, pz designation. So we could call it 3px, 3py, 3pz. We also, for the d's, we have a different type of designation. That would be the 3dxy, 3dxz, 3dyz, 3dz squared, 3dx squared minus y squared. Those I'm not going to make you remember. So you don't have to worry about those. The px, py, and pz are common, but the d's, it's not really necessary. The d's are designated by plane, which plane of the orbital lobes located on it. This is what we call the unhybridized atomic orbital energy level diagram. All atoms would adopt this. All multi-electron atoms would adopt this. However, we could also have hybridized atomic orbitals. Why hybridize these atomic orbitals? Right, we need to minimize repulsions. So if we have a free atom, then it could just be this way. But if we have molecules with bonds and lone pairs and that kind of stuff, then we need to minimize repulsions, and then we see hybridization. Not for everything. The smaller the atom, the more the repulsions are going to be concentrated on that atom. The bigger the atom, the more space there is, and repulsions aren't as significant for big atoms as they are for small atoms. But what we're going to do is we're going to hybridize everything if we can. And so we have the unhybridized atomic orbitals. Can you draw the atomic orbital diagrams for hybridized? How many different hybridization schemes did we talk about? Yeah. So it depends on what the valence shell is, or what the outermost shell, or what the valence electrons are. All the bonding occurs in the valence shell. The core shells don't participate. So if we're looking at the second shell as the valence shell, then it would be the 2s and the 2p hybridizing. If we're looking at the third shell, it would be the 3s and the 3p. Now these third shell orbitals here are a lot bigger, because the repulsions aren't as great. As we get bigger and bigger, like the fourth, the fifth, the sixth, by the time you get to the 7p, those are pretty big orbitals, so there's a lot of room. And so the requirement of hybridizing it isn't so strict. Even in the third shell, oxygen for sure hybridizes, but sulfur, oxygen's like this, sulfur's a lot bigger, has another shell of electrons. Sulfur may or may not hybridize, or it'll hybridize to a very small extent. But rather than getting into it with that much detail, we'll just hybridize everything. If we hybridize everything, then it'll be easier for us. So, can you draw the, let's say we're looking at the second shell, like carbon, whatever. Can you draw the orbital energy level diagram for this? Now, the book only looks at the valence shell, but I'm just doing the whole thing to just show that the cores don't change when they hybridize. And so if we're looking at sp hybridization, it would, sp is 50% s, 50% p, so the energy is going to be right in the middle. And so this is one sp orbital, this is another. This is in n equals 2. The n equals 2 principal. Quantum number there. And so here we'll have our 2 p orbitals, 2 of them that are unhybridized. So can you draw all of them like this for the second? Can you draw the shapes of the orbitals like an S? What's an S? What's a 2s? Bigger spherical plus one other thing, a node. A node is where it goes from positive amplitude to negative. Well, the 1s is all positive amplitude. And so here it goes positive and negative. Yeah. 3s is even bigger with not just one node, but two nodes. So it goes positive, negative, positive. What do 2p orbitals look like? This only has one node, planar node there. 3ds, most of them are like 4-leaf clovers. One of them is going to be like this. P orbital looking with a Google on it. How about an sp orbital? Can you draw what that looks like? Now, I drew these separate. I didn't overlay them. But with hybrid orbitals and unhybridized orbitals in the same shell, we usually draw everything together. And so rather than drawing one orbital, if I just drew one orbital, it would look like that. Okay, there's my one sp orbital. It's kind of lopsided. Here's a nucleus here. There's a small lobe here, but usually that's ignored. That's one sp. And so unlike these, we usually overlay everything. So this is an sp, this is an sp. Where are my p orbitals? Yeah. Okay, there's going to be one p orbital that's in figure 8 here, and another one that's figure 8 that's coming out and going into the board here. And so this would be one p orbital, and this would be another p orbital. And so, unlike our regular atomic orbital energy level diagram, we could overlay everything. But if you start overlaying everything, like for example, here we have our s orbital. So if I wanted to overlay everything, I put the one s orbital like this. Okay, that's good. And then the 2s orbital. And then the 2p orbital. X, Y, and Z. And then the 3s orbital. And then the 3p, X, Y, and Z. And then the 4s orbital. And then the 3d orbitals. Five of those. And then it gets kind of, to be a bit much. And so just for the hybrid orbitals, we kind of overlay them. The 1s orbital we ignore, otherwise it's starting to get too much. I suppose we could do the same thing, just look at the valence orbitals here. But one thing is once you fill a shell, then all of those orbitals add up to a spherical symmetry, say, looks like a ball. So if we look at the 3p orbitals and we fill those all up, then it has that spherical symmetry. And the same thing with the 5ds, even though they all have this clover leaf, we combine all 5 of them, it's going to have what we call spherical symmetry. All right, so you'll need to know a little bit about hybrid orbitals. You aren't going to have to do what we were doing in the lab, filling the hybrid orbitals with electrons, overlapping, all that kind of stuff. You aren't going to have to do that. But I expect you to know we're dealing with atomic orbitals, And what are all the atomic orbital energy level diagrams that we have? Hydrogen and one electron, multi-electron unhybridized, multi-electron hybridized, multi-electron hybridized in sp, sp2, and sp3. Those are all the atomic orbital energy level diagrams. We want to know the atomic orbital energy level diagrams because pretty soon those aren't it. Like for example, here this says orbital energy level diagram. I don't like that title, orbital, because we have two types of orbitals. Do you know what the two types of orbitals are? Well, you might say there's unhybridized orbitals and there's hybridized orbitals, but that's not, there are two types of atomic orbitals. The two types of atomic orbitals are hybridized atomic orbitals, sp, sp2, and unhybridized atomic orbitals. But there are actually two types of orbitals, and the two types of orbitals are atomic orbitals, both hybridized and unhybridized, and something called molecular orbitals. Molecular orbitals we're going to talk about later. But we'll take a look at what we call some molecular orbital diagrams, like this one. This one is a molecular orbital diagram we're going to look at in chapter 11. This one's for carbon monoxide. So what I don't want you to do is I don't want you to get them mixed up. I want you to learn the atomic orbitals very well. Over here on the left, we have the atomic orbital diagram for carbon. Over here on the right, we have an atomic orbital diagram for oxygen. And in the middle, you know what we have? In the middle, we have the molecular orbital diagram for carbon monoxide. What do these molecular orbitals look like? Let's see. All right, these are the molecular orbitals, 3 sigma, 4 sigma, etc. If we look at what the molecular orbitals look like for carbon monoxide, these are what they look like. You know, the red is a positive amplitude, the blue is negative amplitude, so we go negative positive. This is positive here. You can see the different wave forms there for carbon monoxide. These can get very complex. You know, carbon monoxide is a simple molecule. These are them again here. Although these ones look pretty complex. If you look at that 4 sigma star, that's looking pretty complex. But let's take a look at these. This is a molecular orbital diagram for, not molecular orbital diagram, this is a molecular orbital for ethanol. This is just one of them. One of how many molecular orbitals are there for ethanol? Infinite. Do you want to derive all of them? No. You could buy this one. You could buy this one for $15. Somebody made it, animated gift. This is pretty cool too, this one here. Animation. But these molecular orbitals come from the full, what did we have? We had a partial quantum mechanical treatment and a full quantum mechanical treatment of molecules. Do you recall the names of those? Like the full quantum mechanical treatment of a molecule versus the partial quantum mechanical treatment. Okay, the full one that incorporates all the quantum mechanics?
No, that's molecular quantum theory. And then the partial is valence quantum theory.
Yeah. Okay. So there's something in quantum mechanics, there's a light version. The light version of quantum mechanics is called valence bond theory. The light version is applied to molecules. It's valence bond theory. It's partial treatment, What do I mean by partial treatment? What I mean by partial treatment is we retain atomic orbitals in molecules. And so all molecules consist of atomic orbitals, and the atomic orbitals overlap to form bonds. They might not overlap if there's a lone pair or it's empty. But if we want to form a bond, the bond is formed by overlap of atomic orbitals. And so the atomic orbitals are all still there. They're just overlapping to form bonds. We don't have a valence bond energy level diagram. There's no such thing because in valence bond theory, we don't get any energies in there. We can take a guess. It's not the case. If we do the full quantum mechanical treatment, the full quantum mechanical treatment is called molecular orbital theory, actually. Molecular orbital theory is going to give us the energies. Do you see? We're going to get an MO, molecular orbital energy level diagram. And so we can see what these transitions are, what the potential transitions of electrons are. And therefore we can generate the spectrum of the molecule. You know, lots of molecules will have color. Not just molecules, ions too. You can do the same thing for ions, generate the molecular orbital diagram. Now, the problem with what's the problem with molecular orbital theory? You know, if molecular orbital theory is the comprehensive approach, then we should use the comprehensive approach, because then we'll get the most accurate information. Not only the most accurate, but we'll get the complete picture of the molecule, theoretical picture. And that's what we want, because we want to be able to make predictions based on that. But anyway, there's a problem with MO theory. And what is the problem with MO theory? Too much work, right? Way too much work. And not only is it too much work, the calculations are very hard to do. And so to simplify the calculations, they make a whole bunch of assumptions. You know, we'll just assume this. It makes the numbers easier. And so that leaves us with valence bond. And so this is why I call them complementary. Really, we can get rid of valence bond and just do everything with MO. That would be better. But MO is too much work. And valence bond you could do with pencil and paper. Because we don't care about the energies, we're not doing any energy calculations. Valence bond. If we needed energies and energy calculations, we do MO. Valence bond is so much easier. This valence bond, again, we retain the atomic orbitals. MO is much harder because in MO we get rid of the valence atomic orbitals and we replace those valence atomic orbitals with, we don't really get rid of them. You know what we do? We do an LCAO. What does LCAO stand for? Yeah, we do this. We take the atomic orbitals and we do a linear combination of atomic orbitals. This is quantum mechanical mixing of those atomic orbitals. And what spits out of all those atomic orbitals, the linear combination, are molecular orbitals, whole new set of orbitals. And so we learned those. Now the core orbitals stay the same, you know, because the core electrons do not participate in bonding, but the valence will. And so it's kind of like the same thing with the hybridization, but we go extreme, you know, and we get rid of those atomic orbitals entirely. Whereas hybridization will retain the atomic orbitals. So since that's the case, we want to learn both versions. We want to learn the light version, which you can do in pencil and paper, and we want to know the comprehensive version, which we use a computer to generate. Using a computer is very easy, you know, for simpler ones. In fact, students are kind of fortunate. Students have undergraduate students have a lot. They figure undergraduate students don't have a lot of money. And if you're going on They have a iPad version of this, and they also have a phone version of this, Spartan. But when you look at the pricing for this, let's say I want to get Spartan for myself. Let's see how much it is. Single license. Let's say I'm commercial, it's $7,200. But since I work for a school, I can get a single license for $2,400. Pretty expensive, $2,400. We used to have a site license here, but they didn't want to renew it. We had a site license with 16 cores. Oh no, this is 16 cores. Greater than 16 cores, single license. Below 16 cores, it's a bit cheaper. So below 16 cores is only $4,800. I'm not going to buy a 3-year plan. Yeah. All right, so do you see the price? So academic, I can get at 24. If I'm government, I can get at 48. If I'm commercial, like some pharmaceutical company, I can get it for 7,200. But how much do students get it for? Student license, $50. $50. For $50, it's totally worth it to play around with this, either Spartan or Odyssey. For student use only on student-owned machines, cannot be resold or transferred to a different computer. So what they're doing is they're trying to hook you into using, because there are other programs that do the same thing. You have Gaussian, Spartan, you have a bunch. We just had Spartan. But this means high school license means license for the high school, not high school student. This is for all students, high school or college. But $50 is well worth it, I think, for this.
So what is this? Like, what can you do with this?
What can you do with this? I would show you what you can do with it, but unfortunately, I don't have it anymore. They're supposed to load it onto this computer. Let me see. But basically, what you can do with this is quantum mechanical calculations. And so if you're interested in things like this is wrong. I'll tell you what we can do. This is one lab that I made up. Let me see if it's on here. Remember I showed you the vibrations of water?
Mm-hmm.
Spartan, you can calculate those vibrations and the vibrational energies associated with those vibrations. So you can do that. Not only that, you can put the water in a magnet. And once you put the water in the magnet, the hydrogens act like little bar magnets. And then Spartan will allow you to calculate. It's actually semi-empirical because the calculations are difficult. But Spartan does semi-empirical. You know what semi-empirical means? Partially theoretical and partially from observation. And so they just, they get something that close to work and then they fudge factor it so that it works. Basically. But what I had the students do, this is in Chem 1B, I have a lab. And the lab is to use Spartan to predict the acid strength of a series of 5 acids, which is predicted to be the strongest acid and the weakest acid. And then what we do is we go into the computer lab and then model each of those acids quantum mechanically and then see which of those is predicted to be the strongest and weakest, and then compare that to experimental. results. But there are a bunch of other things. A bunch of other things is something called Odyssey. Odyssey, they have different things. Uh-huh.
Well, I was gonna ask about what we know for example is the you know, we're using the single one and the multi-electron one, and you said the hybridization and how do we do
Well,
the hybridization?
The single electron, do you know what that is, right? Yes?
They're the same, or will it the same like? Yeah.
This one, you know the single electron, right? So we have one, we have two, and then we have a bunch, three more for hybrid atomic orbitals. And so it depends on where the hybridization occurs. Is it going to occur in the outermost shell? So is it in the second shell or the third shell or what? And so this would be in the second shell. We had sp hybridization. And typically, where it's going to be the most important is in the second shell anyway. And so this is sp hybridization in the second shell, n equals 2. Could you draw the energy level diagram for sp3 and sp2? Yes or no? No? This is why, in lab yesterday, I was asking everybody to draw from the core to the valence. Yeah. Did you take notes?
I was so confused how you get to
Do you have the diagram for sp2? Mm-hmm.
based on the shape of the structure or is that not?
Well, I'm jumping ahead. I'm jumping ahead because I want to just talk about all the atomic orbital energy level diagrams at once, rather than talk about some of them here and then some of them later, and just rather talk about all of them. And so, if you want to see this in more detail, maybe go to chapter 11. You get it. I think it's in chapter 11. Let me double check. It's been a while since I looked. Eleven three. Here are the valence orbitals. What do you notice about the valence orbitals? One, they aren't showing all of them. What it looks like one, maybe they are showing all of them, but one of them looks funny. You know which one looks kind of funny to me? Do you see, if you look at the valence orbitals, can you recognize the orbitals? If you're looking at the valence orbitals for carbon, what orbitals should you find? Carbon valence orbitals are in the second shell. What are the orbitals in the second shell?
1s, 2s, 2p.
Okay, we're going to have the 2s and the 3-2p. I see the 3-2p. Here's one. Each one's going to have a blue and a red. corresponding to positive and negative amplitude. So here's the P. Oh, let's call this one the PZ. What should we call it? PY or PY? We're going to call this one the PX, and then this one will be the PZ. So we have our three 2p orbitals. Do you see those? And which one are we missing? The 2s. And I suppose this is supposed to be the 2s, but this 2s looks weird because the 2s is supposed to be spherical around the nucleus. You see, it's the way the shadowing is they put this in front of these lobes. It's supposed to encompass all those lobes. Not only that, the RDF is off. You know, this should be further out. The 95% probability boundary should be further out. It should be a bit bigger. But this, I don't expect you to necessarily draw this, although you should be able to draw this. But maybe you could draw a better one than they did. But you should be able to draw that, because what are those? It's a tetrahedral arrangement of what kind of orbitals? sp3. Can you draw that? And can you draw the atomic orbital energy level diagram for that? If yes, then good. If no, then not good. Could you draw it? Okay, that's good.
Wait, so why the 2p orbitals, why does carbon have 3 when it should only have like 2 electrons in the 2p?
They're empty. I mean, they could be empty. All they're doing is they're taking the empty orbitals and then hybridizing it and then filling it. And so this is just the process that we use. We don't base it on how many electrons there are. We just base it on what the hybridization is. So if it says sp3, then we're going to use all 3. If it's sp2, then we're just going to use 2 p's. sp, but we'll still draw. We can still draw all of them. You know, in fact, that's what I want you to do. I want you to draw all of them because of this. This is sp3 hybridized. What does the energy level diagram look like for this? The energy level diagram for this looks like, well, actually, this is the hybridization. So we take these 4 orbitals and we make 4 new orbitals called hybrid orbitals. The little lobe here we completely ignore and we get this. So it's tetrahedral. The energy level diagram looks like this. So we take this is just looking at the valence. The core is ignored because nothing's going to happen to the core. It just stays alone. But I want you to write the core in there. And then over here, we get the 4 sp3 hybrid orbitals. And so one of these was empty, but we went ahead and hybridized it anyway. And it turns out that we ended up putting 1 electron into there. So when I'm looking at this, I want to see, okay, if you draw the atomic orbital energy level diagram for this, what happened to the 2s and 2p? Are they still there or are they gone? The 2s and the 2p unhybridized orbitals. Are the 2s and 2p unhybridized orbitals still there? Maybe they're down here, or are they gone?
2s.
While the 2s and 2p, all these 4 orbitals have been completely hybridized, so they're no longer there. They've been mixed. The only one that's still there is the 1s. The 1s is still here, and then the empty 3s, 3p, 4s, those are all unhybridized, and those are empty, and those are all up there. We only hybridize these, the outer shell orbitals here. Why do we care about the empty orbital? Because sometimes they're not empty. Like in this case, it was empty here, but when we hybridize all 3 of them, is it still empty? No, it's no longer empty to maximize bonding. And so what we ended up doing is promoting an electron up there to maximize the bonding. But it could still be empty, and we care. We care that it's there. And so let me give you a case of this. Here. Okay, this is going to be sp2 hybridized. We don't care what's happening with electrons here. We care what's happening with electrons here. And so here, it's still empty, but it's still there. That empty orbital provides a site for reactivity. And so if you have a Lewis base is electron pair donor. It wants to donate electrons, it's got to have some place to donate them to. And so in this case, that empty orbital provides a space for a Lewis base to come in, and this would be a Lewis acid because it has an empty orbital in which it can be attacked by a base. And so we care about these empty orbitals because that's where we can have some reaction occur when we look at it in more detail. And so here, this would be like BF3. BF3 would be sp2 hybridized like this. And boron has an empty p orbital here. Well, that empty p orbital is perfect for a Lewis base like ammonia to come in and boom, attack it there. When that happens, it converts from sp2 to sp3, so we transition, and that p is hybridized with the other orbitals, make it sp3 rather than sp2, and we end up with a tetrahedral structure. So that's the type of stuff you would do like in organic chemistry a lot more. Probably the second part or the last part of organic chemistry, you start looking at the orbitals and how they interact. And valence bond is quite easy, but molecular orbital is better, you know. And so you'd be doing both valence bond and molecular orbital approaches to reactivity like that. But oftentimes, sometimes these unhybridized p orbitals, if there's an electron there, then we have a chance for forming a double bond, you know, like a sigma and a pi bond, like we were talking about earlier, you know, and they go into that here. So could you draw this? Do you recognize what these orbitals are here? It's a trigonal planar arrangement. Can you tell me what those orbitals are? Those are atomic orbitals, and those would be called sp2. sp2. So and these are, what hybrid orbitals are these over here? These are sp, but this could be mistaken for a p orbital, but it can't. Because a p orbital would go positive and negative amplitude. These are both positive amplitude. You see that? And the other thing is this. If you continue on, let's say in reactivity and this kind of stuff, we have to have positive, when we form a bond, the bond has to be between positive amplitude and positive amplitude. If we try to overlap a positive with a negative amplitude, that's what we call destructive interference, and a bond doesn't form. A bond's got to form from red to red or blue to blue, like negative to negative. It has to be like that. And so this is why you're thinking, why do we care about the positive and negative and the blue and the red? Well, that's the reason why we care. We care because it's going to play a role further down the road. Not right now. For us, we don't really care, you know. It's not that big of a deal, but later on it becomes a much bigger deal. And then we have these two unhybridized P's. These two unhybridized P's can also participate in bonding as well. But for right now, they're empty. Okay. Can you draw those? Or can you recognize them? That's why we're doing all this drawing. This drawing is maybe a little bit tedious, but we're trying to draw it to remember, you know, what they look like and what the energy level diagrams look like. I want you to draw the complete energy level diagram. That way, you know, in the future, you get tired of drawing the complete, you can just shorten it. But if you always draw the shortened version, then you don't know necessarily what the complete version looks like. And then you could also be fooled because sometimes they'll give you the total number of electrons and not the valence. Or other times they'll give you the valence but not the total. And it screws you up because it depends. If they give you the total number of electrons, then you need to use the total energy level diagram. If they only give you the valence number of electrons, then you just use the top part of the orbital energy level diagram. And so there are little things that throw people off. Because all of a sudden, you're only used to seeing the valence, and then somebody throws in the total, and people get it mixed up.
too, like C3, like that level.
Yeah, the shape, the
So
geometry.
we don't have to do like what we did in the lab.
No, you don't. Okay, is that clear? All right, so once we have that, then we are going to fill these with electrons. And filling these with electrons, there are different ways. Did I talk about electron configuration, orbital box diagram?
Yeah. We ended on electron configuration, and we talked about as filled versus as ionized in the condensed form.
Okay, as filled versus ionized. Okay, that's good. So everybody should be able to draw this. I mean, this is chapter 8. And this is like the periodic table right here. First row, second row, third row, fourth row, periodic table. When we fill these, we need to pay attention to the off-bow principle. What was the off-bow principle? Did I talk about the off-bow, Hund's rule, Pauli exclusion? Okay, that's for ground state. For excited state, I can put the electron anywhere I want because it's excited state. But for ground state, the electron should be in the lowest energy. Off-bow principle. And then what's this? Where does the next electron go? Yeah, here or here, it doesn't matter. But it should be same spin or opposite spin. Parallel spin, that's called Hund's rule. And then once we do that, then we have to pair up. No more than 2 electrons here, so I can't put a third electron here because that would violate the Pauli exclusion principle. The next electron goes here, here, and then we fill these one at a time. And everything is normal. Those rules are good until we get to chromium and copper. And so here we're at 4s2. What element is 4s2? Fourth row, it would be calcium. Okay, from calcium we go to, what's next after calcium? So calcium is number 20, scandium. So scandium is this, 4s2, 3d1. So we can write the electron configuration in different ways. One, if we fill up to the third shell, then that's argon. And so the easiest for scandium is argon core, 4s2, 3d1. How many valence electrons does scandium have? Scandium has 2 valence electrons. And so we could write this as filled, or we could write this as removed or ionized. And so we're going to ionize the outermost electrons first. The outermost electrons are going to be the n equals 4. So n equals 4 is further out from the nucleus, and n equals 3. And so these would be the valence electrons. It has 2 valence electrons. Those 2 valence electrons can be taken off without too much difficulty. Metals have loosely held electrons. Metals are easy to oxidize. And then we're left with 3d1. Do you think it's going to be hard to remove that 3d1? It turns out it's easy. And for scandium, there's only 1 charge. All 3 of these electrons are pretty easy to remove, but the 4s go first. And the 1 charge on scandium is +3. It's fixed charge to +3. Otherwise, you'd say +2 and +3 are the common charges for scandium. Most of the transition elements are going to have +2 and +3. +2 because of the 4s electrons here, even though the 4s are lower in energy. So this is fine. After scandium comes what? Titanium. What are the common charges for titanium? Now, titanium is not +4. +4 is too high. And so for titanium, we're going to have I'm gonna save some work here and just call the 1s2, 2s2, 2p6. It's our argon. And so for titanium, we have argon 4s2, 3d2. We're gonna flip this around to get it in terms of valence. And so we go in numerical order, 3d2, 4s2. How many valence electrons? 2. So plus 2 is a common charge for titanium. What's another charge for titanium? Another charge is plus 3. And another charge for titanium is titanium plus 4. We remove all of the electrons. Plus 4 is a very high charge, and it's not so easy to do. But you can stabilize it with bonding it to something. And so titanium plus 4 is actually pretty common. Or titanium 4, we should call it. But titanium has plus 2, plus 3, and plus 4 as its charges. Some of this, chemistry is part empirical and part theoretical. And so sometimes we just look up, what is the most common charge on Wikipedia or elsewhere. So we look at the oxidation states. What are the most common charges for titanium? Plus 2, plus 3, and plus 4. Does that make sense? Plus 2, knock those two off. Plus 3, knock one of these off. Plus 4, knock two of those off. Okay, after titanium comes vanadium. Okay, vanadium is going to be argon 3D, or actually not 3D, let's go 4s2, 3d3. 4 argon, 3d3, 4s2. So tell me what the common charges for vanadium would be expected. What would be expected? Plus 2, plus 3. Those would be probably the two most common charges. And in addition to that, what else? Plus 5?
Yeah.
How about plus 4?
Plus 4 too, but wouldn't
Yeah.
plus 5 be nice?
But yes, it would be nice, but it's harder. Each successive electron you remove, it becomes harder and harder to take another electron off. And so it depends on how powerful the oxidizer is. If the oxidizer isn't so powerful, then plus 2. The more powerful the oxidizer, plus 3, plus 4. You'd have to have a pretty powerful oxidizer to get it to plus 5. And so we see variable charge depending on how strong the oxidizer is and how well that charge is stabilized after formation of that charge. So we go plus 2, plus 3, plus 4, plus 5. Those are the oxidations, and probably plus 2 and plus 3 are the most common. You'd expect with vanadium. All right, then let's go to chromium. Now, chromium, what do you expect? Well, for chromium, I'd expect this. 4s2, 3d4. 1, 2, 3, 4. And so for chromium, we expect argon 4s2, 3d4 for chromium. So that's what's expected. And, these quantum mechanical calculations are difficult. What was expected wasn't what was observed. What was observed is this. Argon 4s1, 3d5. That was observed. How did they observe it? Do you know how it was observed? I forgot to mention this in the morning class. But how can you tell the difference between a 4s2 and a 3d4 versus a 4s1 and a 3d5? The way you can tell the difference is in a 4s1 3d5, we'll have 6 unpaired electrons. 1, 2, 3, 4, 5, 6. Each of those unpaired electrons acts like a little magnet. Versus if the electron configuration were 4s2 3d4, we only have 4 unpaired electrons. And so it would be a weaker magnet. And you can measure how strong the magnet is by using something called a Gouillet balance in physics. And by measuring how strong the magnet is, they determine that chromium does not have 4 unpaired electrons or 4 unpaired spins as predicted. Chromium has 6 unpaired spins. So in order to get its 6 unpaired spins, they had to violate what principle? They had to violate the off-bound principle. And so what we're doing is going to cost us energy. We're going to promote an electron, but where's the return? You know, we don't want to, there's got to be some kind of payoff in this. And do you know what the payoff is? The payoff is this. If you combine all 5d orbitals, do you know what it looks like? If you combine all 5d orbitals together, overlay them, you know, when you look at them individually, one on one, they look like a clover leaf. But if we combine all 5 of them, you know, pretty soon, you know what it looks like? It looks like a ball. This is what we call spherical symmetry. And what would this be? Would it be like a half ball? Like this? And so we'll just cut this in half. Is that even possible? No, that's not possible. You know what it's going to look like? Rather than a full ball like this, it's going to look like a mini ball. Because each of these orbitals will be half filled. And so we're going to get a little mini ball, which still is spherical in symmetry. That spherical symmetry has some implications as far as the energy is concerned. It's going to be more stable. And so one way of trying to visualize this using cakes is like this. If you have a cake, and let's say I want to eat half today and half tomorrow. Normally you just cut it down the middle, like this. But that's not what happens with these d orbitals. We still have the 5 d orbitals, and if you add up 5 empty d orbitals, it's going to be spherical. If we add up 5 half-filled d orbitals, it's still going to be spherical. And so rather than cutting it like this, we cut it like this. And so there's 2 ways. We can cut it like this, or we can cut it like this and then get half of it. And so this is half filled. This is filled. And so let's make a long story short here. Half filled is more stable versus half filled with a slice taken out. So this would be D5. D4 would be half filled, and then you cut out a slice. The slice is going to be 1/5. And so we lose that symmetry here. That would be D4. The other configuration is D10. D10 is completely filled. And so D10 is also stable. And so chromium, the reason why an electron gets promoted is to get half filled at minimal cost. Vanadium would require 2 electrons. And 2 electrons is too much to promote to get half filled. So it just happens for chromium. We can promote 1 electron. And the same thing for copper. Copper, we predict, is going to be 4s2, 3d9. And so 3D9 is just one electron short from filling. And so what in copper, what's observed is 4s1, 3d10. And that way we can have a filled D subshell. So half-filled D subshell and a filled D subshell have additional stability. Therefore, chromium and copper are two exceptions that you want to know in filling. Otherwise, there are more exceptions, but we aren't going to worry about that. Two important ones you should know are chromium and copper. So know those two. Okay, we're out of time here. Looks like so. Stop. If there are some questions, I'm seeing around. So if there are questions, you can see around. Are we doing lab tomorrow?
Are we turning in a lab?
You don't. If there's an exam on the lab due date, then you can postpone the lab. But if it's experiment 2, you should do the experiment 2 calculations because those are chapter 7 type calculations. So you should know how to do the chapter 7 type calculations. But you don't have to turn it in. You can turn it in next lab period if you want. If you have it done, you can turn it in. Some people I know have it done. Okay, were there any other questions?